Joseph Mani. She's one of our most recently hired faculty members in the budding Earth and Climate Science research group. She's a climate researcher. She works in climate dynamics, tropical variability, and numerical weather prediction. And today she'll tell us about the use of mathematical methods in numerical weather prediction.
Thank you, Kanika, and thank you for inviting me to the symposium. So it's an opportunity to talk to you about numerical weather prediction. So I'll basically give you an overview of what it is, like how it has evolved over the years, what is essentially weather prediction, what we try to do, and what are the challenges, how do we address it using mathematical methods. So I won't go into deep of any of those methods right now, it will be just an overview talk. So when we say weather, most of you will recognize it as the mean state of the atmosphere at any particular time, right? What is the temperature, what is the pressure, how much cloudy it is, how much rainfall is happening, those kind of things. So this would essentially be the common man's perception of weather. But for a person studying atmospheric science or meteorology, weather is all this active, vigorous activity going on in Earth's atmosphere each second. So all those clouds moving, all those bursts of clouds aligning around the equator, everything constitutes weather for us. So little bit into the history of weather forecasting, how it happened. So I won't go too long back, but first written record of atmospheric processes is dated back to 340 BC by Aristotle's Meteorology, where he tried to understand what is rainfall and what is precipitation and everything. And there were other pioneers like Galileo Galilei who discovered the thermometer to measure the atmospheric temperature. Then there is Torricelli who wanted to measure what is the mass of the atmosphere weighing down on us, that is the pressure. And the Torricelli discovered the barometer. Then there's Blaise Pascal. We know Pascal is the measure of, yes, pressure, right? So Pascal is the one who discovered that pressure decreases in the atmosphere with height. And Edmund Halley, he's the same person as known for Halley's Comet. He was the one to discover that the atmospheric circulation, how is the surface wind patterns and how is the upper level wind patterns. And Benjamin Franklin, the politician as well as the scientist, he was one of those who speculated that these weather systems, the clouds we see moving, are indeed forced by large-scale systems. So he kind of speculated, he didn't really give any proof. So all this happened in the 15th to 17th centuries, and when it came to the 18th century, people had started actually measuring the atmospheric conditions. Like they started making measurements of pressure, temperature, and all the atmospheric variables, wind, taking wind measurements and so forth, and they started plotting it on charts, what we call the weather charts. So that saw the advent of what we call synoptic weather forecasting. So this is an example of a weather chart, and the lines are called ISO lines. So they make measurements at different points and join together points which have the same pressure or the same temperature. So here they have plotted together the points having the same pressure. The contours give you the same pressure regions or the isobars. So from here they identify where are the low pressures and where are the high pressures in the atmosphere, and they put together yesterday's chart, today's chart, and try to make intuitive predictions about what will be tomorrow's chart. So it was nothing scientific, it was only based on, it was more like an art and based on the experience of the forecaster. Like he was just making assumptions or doing like small extrapolations to what it would be. So it was nothing to do with mathematical applications of physical science to meteorology. So the first person who tried to do or bring in maths into meteorology was Yerkins. It was a Norwegian mathematician, and he thought that given the basic atmospheric initial conditions, since it is governed by physical processes, we should be able to predict the future state knowing its equations. Okay, so using mathematical equations, we should be able to predict the future state or make weather forecast mathematically. So he identified what are the prognostic variables, like what all do we need to make such forecasts. We need to make measurements of what all variables. He identified those variables, and he also identified the thermodynamic and hydrodynamic equations which would explain the atmospheric evolution. So that was right. Whatever he identified were like the mass continuity equation, the momentum equations, then there is conservation of water, conservation of momentum, conservation of energy, and the ideal gas equation. All these equations, what Beer gets put forth, are still used. There is nothing changed. So whatever he identified that these are the equations which govern the atmospheric evolution stays forth. But there is no analytical solutions for these coupled partial differential equations, and we could not solve it. And during at that time, it was like 1920s, there was no computing power to try to solve it numerically. So numerical solutions were not possible, analytical solutions were not available. So what he tried was to solve it graphically. So some effort was done to solve these equations graphically, but there was no success. So it took a while, and it was later on the British scientist Richardson who used finite difference approaches to solve these primitive equations numerically. So you convert the differential equations to difference equations and solve it numerically. So, but this is a challenging task. We are going to do it globally at different points, convert it into difference equations and solve it. It is a very challenging task, and it requires computing power. Again, computing power was not there. Richardson employed about like 10,000 people to do it by hand. So that challenging task they did for like 2 time steps or something. But even though the equations were perfect, the results were very dismal. Within couple of time steps, they saw like the pressure vary by like 14 millibar or something, which is not normal, which is an anomaly, just wrong. So this was the first failure, but people took note of Richardson's effort. But we had to wait, the meteorologists had to wait for 30 more years to take off from there. And we had to wait for the advent of computers. That again, contribution from one of the greatest mathematicians, Newman. So the father of computer is also a great mathematician who is known for, I think, graph theory and algebraic, like quantum physics, some contributions he has made. And he is also the father of mathematical computers. So he was developing this highly specialized computing system in Princeton, and he developed a project called Numerical Weather Prediction Project. He identified that computing is a very big requirement for fluid dynamical problems, and there were like 3-4 areas he thought which would benefit from a supercomputer. So the ENIAC machine was developed, which was our first kind of supercomputer, and there was one main project was assigned for weather prediction. And the person who headed was Jules Charney. So he was the person who headed the meteorology project to try and see if we can try and solve the primitive equations using this ENIAC model. So Charney was now put up with a challenge. Richardson had already failed solving it like numerically. So, but people over time, they understood why Richardson had failed, because there were like imbalance in the initial conditions given to those equations. Those were not balanced initial conditions, and that was giving to instability in the system, which was giving wrong results. There is also something called computational instability in the system, which means that we have to constrain the time steps of integration based upon the length of the grid. So if you are going to use a bigger grid, you have to reduce the time scale. The time scale of integration has to be very small. So those were the 2 mistakes Richardson had made, and people understood what to do. But still, with this computing system, Charney was faced with a challenge because it was not enough. We could not reduce the time steps to very small time steps in order to reduce the unwanted high frequency waves in the atmosphere. So there is gravity waves and sound waves which are not useful for weather. So we had to filter them out somehow to make useful predictions. It was those waves which were causing faulty results in Richardson's model. So Charney used an alternate approach. He filtered those differential equations, and he made predictions using those filtered differential equations which did not have those high frequency fluctuations, and it was much more successful. So this kind of gave the push for numerical weather prediction, and for some time people were using Charney's approach of using filtered differential equations for weather prediction. But it was still not true. When we are filtering out something, we are also filtering out something which is required. In addition to sound waves which are high frequency, there might be useful weather signals which are in high frequency. So later on, people went back to the original Primitive equations and tried to solve it. So the development of such comprehensive, first dating back to 1954, it is the Norwegian military which actually started producing operational weather prediction. And from then on, it has evolved, and after 1980s, the growth has been phenomenal. Now it is much better than our old way of prediction. Numerical prediction has taken over. So initially, when Charney had tried to do that calculation using ENIAC machine, it took 24 hours to do a 24-hour integration. So practically there was no value for that skill, because by the time the machine integrated over 24 hours, already that 24-hour period is over. So, but slowly the machines evolved. It's together like hand in glove thing, like both computing capabilities as well as the prediction capabilities went on improving, and this is one of the finest achievements of the 20th century for the meteorology community. And I will here have cited what is Bjorken's thoughts on his failure. So this is a very motivating thing to think of for anyone in research, I guess. And this is improvement of skill over years for the weather prediction. So this on y-axis you have the skill scores, and on the x-axis you have the years, how it evolved. So just consider this is a day 10 forecast. Like 10 days ahead, we are trying to make the prediction of the weather. There was practically no skill, like less than 30% skill until like 1999 or 2000. But now it is close to like 40 to 50%. So now we are able to make useful weather prediction up to 10 days in advance. Okay, so this is a very big achievement which happened over 50 years, and it's still going on improving, but there is a limit. I'll come to that. So what we do? How do we make the predictions? Basically, I have told you the basic skeleton of weather prediction models remains the same. Whatever Bjorken's had put forth, the momentum equations, or what we call the Navier-Stokes equations, conservation of energy and water and mass, and then there is the ideal gas equations which connects the pressure, volume, and temperature. So this 3D, like these equations are solved numerically on 3-dimensional grids all across the surface of the earth and also vertically. So there will be a number of vertical levels where we solve it, and all around the globe. So that is a function of like x, y, and z. And the grids itself has evolved over many years, the shape of the grids. The certain shape of the grids facilitate accurate calculation in different regions, and also like faster calculation. So people have been trying out different shapes of the grids, where how do we place the grids of measurements or grids of initialization in the models. And this only one criteria constrains this, which I said, computational instability. So computational instability can result if this criteria is not taken care of, that the time step of integration should be less than the grid spacing divided by the velocity. Now, closer. Now some of the challenges or the more detailed problems in weather prediction, or like solving the equations over grids or finite differencing methods. That is a base. What are the other things? So this is a grid, zoomed into a grid right now. So what you see here is like in the first talk, we heard that in biology we have like multiple scales of changes. Just like in atmosphere, there's like millions of scales of changes, right? From millimeter to 10,000 hundreds of kilometers. So even if you are considering like a 30 by 30 grid scale, there will be multiple processes which does not get resolved. You don't see what is happening inside this grid. So this is a grid box. You can see what is happening in the boundary, but what you cannot see what is happening inside it. So even if you go to 1 kilometer resolution, you will still miss out most of the things like turbulence or convection or those fine scale processes. So this requires that we cannot neglect it, because this includes turbulence, which is important for how heat is transferred from the Earth's surface to the atmosphere, convection, and cloud formation. Then there is radiation effects. All this comes in or happens within a grid. If you are not taking them into account, the system is not closed. So we have to somehow take it into account that, and for that some statistical formulations are used here. So what we use is, we try to formulate the statistical effects of these unresolved processes using whatever we can resolve within the boundary. So this again is a mathematical and a very challenging field called parameterization. So people parameterize convection, try to parameterize radiation and turbulent fluxes. Second challenge is the initial value problem. Weather prediction is essentially an initial value problem. How well we measure the initial conditions is very important to make sure we make the good prediction. So if we have to prescribe the initial conditions of all the dependent variables, we need to know that, right? So, but we don't have a measure of all the atmospheric parameters on every point on the globe at multiple levels. That is not possible. So whatever measurements, we have multiple platforms of measurements on the land, on the ocean, satellites, and also like on the upper air. So different platforms of observations are there. Problem with all this is it is inhomogeneous. We don't have in both in space and time. We have spatial as well as temporal gaps in the measurements of atmosphere. So this will cause a problem in initializing these equations. So this is a challenge, and we have to do so. That is one of the biggest challenges for the mathematical sciences. Like, how do we put in this this big data into sophisticated models? So that is done, and NWP, that is numerical weather prediction, also demands that we should have better ways to incorporate or assimilate the data, whatever we are having, in a balanced way to the models to make useful predictions. So that will include what is your first idea. If you don't have data at one point, what is your idea? You just interpolate it. But just interpolating will not solve the problems. It has to be balanced. There should be a balance. It is a physical system. You cannot just interpolate and put something. So there should be a physical way of doing that. That is what we call data assimilation. So this is, simply speaking, it's a complex method which involves variance analysis and some amount of interpolation also. So what we do is they make short forecast using the model, and this star here is our measurement or our observation. And they try to bring this trust or nudge this forecast to the observation, get it closer to the observation using variance analysis, limiting the error between the predicted and the observed. So each time step they do that, and they get the analysis, or we just use for initializing the model. So when you make a measurements, you don't just feed it into the model, you do data assimilation and then feed the analysis into the model. So this is a very demanding field of science which requires mathematical applications. Again, so initial conditions brings us to the next problem, is the predictability, limit of predictability. So if I told you there is problems in initial conditions, we cannot get perfect initial conditions. We cannot resolve everything properly. So all that indicates that there is uncertainty in our measurements of the atmospheric state. So uncertainty will lead to predictability limit. In a nonlinear dynamical system, if there is even small uncertainty in prescribing the initial conditions, that will eventually lead to very diverse results. So the predictability of the system is limited. So that is true for the atmosphere, and it is known as a chaotic nonlinear system, nonlinear system. So to put it straight, so Ed Lawrence was the first one who proposed this, and he's the father of chaos theory. And he stated that two states of system differing initially by small observational errors will evolve into two random, two states differing as greatly as two randomly chosen states. So this means that if you make a prediction from two slightly different initial conditions, after a while the forecast will be so different as any two random states. That means such a prediction is fruitless. So that is the predictability limit, and for the atmosphere or the weather prediction is about 2 weeks. So this is a very famous quote by Lawrence. It says that there's a flap of a butterfly's wing in Brazil, set off a tornado in Texas. So it doesn't really mean that the butterfly is going to cause a tornado. No. It means that errors as small as the flapping of a butterfly's wings can cause or not cause, lead to a state which is having a tornado and a state which is not having a tornado, two widely different states. So there is the sources of errors in the multiple sources, as I said. In the numerics, whatever we are doing the calculation, it is prone to errors. Rounded off to like 4 decimal place, 5th decimal place, doesn't matter. Even that will finally cause big errors. This and our understanding of the physics, convection and radiation and turbulence, whatever is happening within that itself, we cannot see it properly, we are parameterizing it, that is leading to errors. Initial conditions, we don't have measurements everywhere, that is again leading to errors. And the lower boundary conditions, how the surface is seeing the atmosphere is seeing the surface. But people have put to use this understanding also. So the weather forecasting community earlier was making predictions from one initial condition, they run the model and they get a prediction. But they know that that initial condition has got some uncertainty. That is not the true initial condition. It has got some error. So instead of making one forecast from one initial conditions, they make multiple initial condition, multiple forecast or probabilistic forecast, what we call. They make multiple forecasts from very close by initial conditions to that true state. So instead of just one deterministic forecast, we have multiple probabilistic forecasts. So even if we miss something in one deterministic forecast, we will get the probability of having that weather state. So this is provided a market like development in that community. This happened around like 90s, which people started using multiple forecasts for tropical cyclone prediction or even predicting the El Nino or events like that. So it is much useful than having one single forecast. So it is putting to use of our limitation. So then I will list some of the things which will require further mathematical methods, development mathematical methods. We need to have like more computationally inexpensive and accurate mathematical methods, schemes in models, which is an active area, and people or modelers are trying every day to do that. Better initialization and data assimilation methods. Now they use 3D variable analysis, 4D variable analysis. Still, the results are sometimes good and sometimes bad. So that again shows that, and we are getting data from unconventional sources nowadays. There is a deluge of data. Computation capability is much, much better. So we have to incorporate and find better ways of assimilating this into the models. Better ways of making probabilistic predictions. So how do we choose these different initial conditions? That's the question. Which is the best way of making those ensemble or group of forecast? And this is the most recent advance in like weather prediction is understanding that some part of the system is deterministic, but there is amount of stochasticity in the atmosphere, stochasticity or randomness. So some amount of turbulence and some amount of convection in the atmosphere is accounted to stochasticity. So people are trying to now put this stochasticity into the physical processes in the atmosphere, and that is a different area of research which requires mathematical formulation. And to wind up, I put up this impression of Richardson's forecast factory. So when he put up the equations of atmospheric model, he thought like 64,000 people would have to sit together, like in like multiple levels of a building, keep on solving it, because he didn't imagine that we would have computers in the future. So then they would sit around, work in the same pace, so and do it parallelly. So that was the initial idea of parallel programming or parallel computing. And he thought at least we would need 64,000 people to do the weather prediction. But right now, our supercomputers is like 10 billion times of Richardson's estimate. Still, we are not able to do that. Okay, thank you.